procedure of going to the dentist, every element of that is horrible.
People who are dentists were fully
also like a dog. I like the person to vet, but I don't like the process of going to the vet.
Going to the vet, I'm sure. That's like, for me, going to the dentist is like a dog going to the vet, I'm sure.
Yeah.
Like a poorly trained dog, but you're like,
You sound exactly like a dog.
yeah. I'm just like, no, I don't want to go. No, I don't want to go. Okay.
Don't poke it at the dog.
All right, so let's look at 20, because I want to show you that idea from yesterday, which was this. So what's momentum? Momentum is mass times velocity. So the total momentum, this is what we derived, is the total mass times the velocity of what? The center of mass. Okay? So watch how easy 20 is. Okay? So for 20, it says you've got two blocks. So block A is at rest. Here's A. 15 kilogram block at rest. And then block B is a 10 kilogram block that's traveling to the right at 20 meters per second. Okay, watch, that's amazing. Like, oh, it's gonna be so confusing, right? No, watch how easy it is. The total momentum is, you go mass times velocity, right? So mass times velocity, and then you add his mass times velocity. Isn't that nice? So 200 kilograms times meters over seconds. Is that a yeah?
Yeah.
Make sense? So now, what's the velocity of the system's center of mass? Well, we're gonna use this formula. The total momentum is 200. The total mass is 25. And then the center of mass is what we're going to, center of mass velocity is what we're solving for. And so it turns out it's 8 meters per second. Pretty poggers? What did he say?
I said painless.
Painless, yes, painless, exactly. So as you can see, now why is this less than 10? Because like this is 20, so you might reason out that if these are the same mass, the center of mass would be halfway, so you'd have maybe 10 meters per second, but since he's heavier, that kind of biases the center of mass towards that block. Cool beans?
So what are they, like, I was looking at 19 before class, what are they like asking you to find there?
Well,
Like, it's the relationship between M1, M2, V1, V2.
yeah, so use this. So what's the total momentum of the system? It would be M1 times V1 plus M2 times V2. The total mass is the quantity M1 plus M2.
Okay.
And they're saying that this, if the center of mass is stationary, right, this is 0.
Yeah, okay.
So that makes the whole right side 0.
Got it.
And you're basically going to have, effectively what that means is the total momentum of the system is 0. So M1 V1 is equal to the opposite of M2 V2.
Gotcha.
Right, Trenton? Trenton knows. He knows what's up. So 21 through 24, I hope will be straightforward for you. I want to cover 25. Yes, it is. Well, nothing's necessary, Trenton. We're going to do it. Mr. Trenton. What would you be doing, Trenton? What would you be doing right now? If you say sleep, I will go through the ceiling.
No, I slept plenty last night.
Okay.
I probably practiced guitar.
Ooh, that's lit.
Good job.
What kind of song?
It's a good question.
What?
So that's a good question.
Still $80.
Whatever gets my fingers moving.
Play some Black Sabbath. Yeah. You like Black Sabbath, Julia?
Oh, yeah.
Do you?
I'm not sure.
That's kind of boomerish music for you.
Black Sabbath
is
What would a black Sabbath?
White Sabbath. Oh, sorry.
A band from the late 60s and early 70s.
That's why I was only like.
Okay.
If you said Brown Sabbath, I would not be really hard. I like Dirty.
I'm still getting blinded. Yeah, I don't want to block the sun, but I'm getting destroyed by facts and logic. Well, hopefully this.
You can keep just one.
Huh?
You can keep just one.
You know, actually, I brought these, so I'll just.
Yeah.
Oh.
Looks like Alec yesterday.
Yeah, Alec in film was wearing sunglasses.
Just like that, the whole time in film.
There we go. Oh, yeah.
There you go.
Yeah. Someone asked Mike.
So- What class was I talking to with the hat thing? Was that calculus? I can't remember what I was talking about.
I think it's like
no,
no.
you yelled at Winslow yesterday for the hat.
Yeah.
So, yeah.
Anyway, I'll just go around like this from now on. Okay, so
No.
look at 25. 25 is kind of a long problem, and the goal is to. There's a big lesson here. There's a big idea that I'm trying to communicate to you through this question here. So you got two blocks that they're traveling in opposite directions, right? So 25. So here's where they're traveling along this track. Let's call this, we don't really need we could make a position system, but we don't really need to. So this is so block A is 30 kilograms, and he's traveling to the right at 10 meters per second. And then you've got block B traveling to the left at 5 meters per second. And I made it negative just to remind me that I have to treat this momentum as negative. Okay. Let's do part A. What's the velocity of this system center of mass? That should hopefully be pretty easy. I just do this. P total equals M total times the velocity of the center of mass. Total momentum would be 20 times negative 5, right? Mass times velocity, plus 30 times 10. The total mass is 50. And we're going to solve for that center of mass velocity. So we get 300 minus 100 is 200. So that's a nice number. All right. How do we feel about that? Make sense? So let's think about what that means. I want to make sure no one's confused about the meaning, right? That means if you could somehow put a little dot where the center of mass happens to be at all times, that dot would be moving to the right at 4 meters per second. Are there any questions on that? Okay, great. So now it says, suppose that Bob is on a cart. So let's put Bob here. What we're going to do is, I'm going to try to draw this. So Bob is going to be traveling along this axis, and he's traveling at this speed. So Bob is traveling 4 meters per second. Is everyone still with me? Okay. So the first question is so this is in Bob's reference frame. This is what one of Einstein's most famous ideas was: everything is relative to what reference frame are you in, right? If you're moving really fast, if you're in your car going really fast, Mr. Mukow seems like he's going really fast, right? Right? If you're going 50 miles per hour and the cow's running 2 miles per hour the opposite direction, from your perspective, from your reference frame, the cow looks like he's going 52 miles per hour, right? So
I'd be scared.
in Bob's reference frame, so what Einstein got famous, one of his famous ideas was if you take that concept and then apply like the fact that the speed of light is always constant in any reference frame you're in, no matter how fast you're moving, you get all these cool results that they call it special relativity. Then he expanded that to like describe his theory of gravity, which is general relativity. So hey, some fun reading for you if you want. Probably find some cool YouTube videos that explain it. What?
The cow.
Well, what he showed was that for the cow, that's true, but for light, it's not. If you're going 50% light speed and a beam of light is coming towards you, you don't measure that light is going faster than the speed of light. You just measure it the same. But there's a lot of consequences to that fact. So you can show how. The other good example is if you're in your spaceship going. Here, quick example. Classically, if you're on a train, right, and you throw, say the train's going 50 miles per hour and you throw a ball 40 miles per hour, from a reference frame outside the train, the ball's going 90 miles per hour. From the reference frame inside the train, the ball's going 40 miles per hour. But what he showed was, with the way light works, is if your train's going, say, 60% light speed, and a beam of light is shot out, it doesn't go 160% light speed, it just goes light speed. And so there's a whole bunch of like interesting consequences. You start analyzing that mathematically, you see like, wow, that actually means things like time slows down in the fast train, things like that. You also saw Interstellar.
Yeah.
That's a little bit different. The time dilation in that movie was because they're in a really strong gravitational field. You didn't see Interstellar? Who said that? Oh my
I haven't seen it yet either.
God. You gotta watch Interstellar.
Yeah.
Maybe at the end of the year we can watch it.
There we go.
But there's a thing in the movie where like the guy on the ship, a lot of time passes for him, where and the people outside the ship, not much time has passed. So there's a time dilation. Anyway, sorry, let's get back to this. Sorry. So in Bob's reference frame, we're back to classical physics here. That will be much easier to deal with. Classical. Okay, Galilean, right? Hashtag Galilean. In Bob's reference frame, what is the velocity of block A in Bob's reference frame? Who knows the answer? Close, sort of. You're in the right. It's 6. You're not going to add them, right? Because if you're chasing this, right? Imagine that you're in a car going 60 miles per hour, and the car next to you is going 62 miles per hour. From your reference frame, that a car appears to be going 2 miles per hour.
And
Right?
that's the block B, since it's negative, it'll be 9 meters per second.
Very good. -9.
Going away from me.
Is everyone okay with that?
But from our perspective, he would block A. No, we don't.
From our perspective, Bob's going 4.
Okay.
Bob's going 4. A's going 10. B's going -5. But now put yourself in Bob's shoes. Bob says, "I'm not moving." That's one thing. Like if you're in your car on the highway, you don't really feel. If you close your eyes, you don't really feel. Like you're in the passenger seat, not the driver's seat. I'm saying you don't feel like you're moving.
Okay.
Short of there's vibrations in the car that kind of let you know that you're in the car, but like you don't have any. If I put you in a perfectly smooth train and with no windows, you would have no way of knowing how fast you were going, right? Once you were at that speed, I'd be like, how fast do you think you're going? You have no idea if you're still or if you're going 100 miles per hour or 200 miles per hour. That's the idea. Those Japanese trains that go like 200 miles per hour. Yeah, like you're in the train. Sure, there's acceleration that gets you up to that point, but if you do it gradually enough, once you're fine. You're not going to feel that at all. So anyway, everyone okay with these two numbers?
Works for me.
So then, what from Bob's reference frame, this is the interesting part, I promise, it's interesting. What is the momentum of block A from Bob's perspective? Mass times,
So I guess Bob doesn't have to.
his mass. No, Bob's just an observer. He's going to look at block A and say, I'm gonna multiply A's mass times velocity. So A's mass is 30. And what's block A's velocity from Bob's perspective? 6. So what's the momentum? 180 kilogram meters per second. How about block B? Block B is 20 kilograms multiplied by -9. Look at that. So, does that make sense? What's the answer to D then? What's the total momentum of the system from Bob's perspective? 0. So the total momentum now that I actually considered putting the general case on this, but it gets really cluttered. So I just picked these numbers, so they worked out kind of nice. So maybe you can take, I guess if you want to do extra credit and show that. So in general, this is always true. Picking an M1, you have to pick an M1, an M2, a V1, and a V2, and show how no matter what values you picked, if you are traveling along the center of mass reference frame, then the total momentum of the system has to be 0, that's pretty interesting, right? That's a general result. That works. It's not just for 2 blocks. It could be 100 blocks. So if you had 100 blocks traveling in all these different directions in 3-dimensional space, and you tracked along the center of mass, if you moved with the center of mass, from your perspective, the total momentum of the system is nada. Cool beans? Cool beans for all. I actually can't even see the screen anymore because they're polarized.